as was already mentioned, this is actually my fourth straight challenge, the one that I participate in. This is a special one because it's in honor of David Johnson. So David had a big impact on my career, starting from, as Marisa said, like I interned with his team 20 years ago. I co-organized the Dimex Challenge with David, I guess 7 years ago now. And perhaps most importantly, I think David was a big champion of experimental algorithms and algorithm engineering as disciplines, and those are the disciplines that I identify myself the most with. So my career would have been very different if it weren't for David. So it's a privilege to be here and to help honor him. And as Mauricio mentioned in his talk, he was just all around great guy, great person to be with. So I'm happy to be here. So let's go on to the talk. So I'll talk about last mile deliveries at Amazon. This mostly, the talk will be related to AMZL, which is Amazon Logistics, which is Amazon's internal provider. So whenever you have a package, you order a package from Amazon, you may get this package through USPS or UPS or Royal Mail or DHL or whatever, depending on where you are, or you can get it from AMZL. AMZL has hundreds of delivery stations worldwide, and it's responsible for delivering to final customers. The basic setup for its operations is quite simple. So you have the station, shipments arrive at the station through the night. So they come in very large trucks, line hauls with like thousands of shipments that are coming from fulfillment centers and sort centers. They arrive through the night, and in the morning, you have to have routes that are prepared to leave to deliver to the final customers. And these routes are in smaller vehicles. They may have anywhere from like 40 to 200 or 300 or more packages. So these will be vans and personal cars and so on. Amazon AMZL is a very fast-growing business. It's one of the biggest carriers in the US for packages already. It has grown, like the number of stations has grown by a factor of about 3 since 2019. And AMZL already handles the majority of the US deliveries for Amazon, and it's also a big fraction of the packages delivered in other geographies around the world, or other countries around the world. So, as you can imagine, since I'm here, we must solve some version of the equal routing, in the sense that we're going to have a bunch of shipments. A very large station may have like tens of thousands, in some cases more than 100,000 shipments. We need to partition the shipments into routes and sequence these shipments. This talk will not be about finding the solution to the problem, so I'll mention it. But it's more about what I learned since joining Amazon, is that the solution is only part of the problem. Like kind of defining the problem itself and everything that goes around it is extremely challenging, and we actually spend a lot of our time on things other than actually trying to find the best algorithm to solve the problem that we have. So we have to worry about things like what are the kinds of inputs that we have available, how good these inputs are, what are other inputs that we can get, what kinds of trade-offs we have to make to find a plan that looks good for all the use cases that we have. How do we make sure that whatever optimization problem we're solving actually fits well with all the processes that happen before and after routing in the fulfillment flow. And even the human element plays a big role in the kinds of things that we do. And of course, we have to make simplifications. And when we have these kind of, when we focus on the algorithmic research, we tend to make simplifications and say, oh, this is a minor implementation detail, or this is not something that I need to worry about at this point. But for example, like on the right side of the screen, we have like a standard benchmark instance for the CDRP, and we have a bunch of points on the plane, and we have kind of well-defined transit times and capacities and so on. But this embeds a lot of simplifications and a lot of assumptions, and especially as we get denser routes, these kinds of assumptions start breaking. And so this talk will be about like the kinds of things that we have to worry about when dealing with these problems in practice. So let's start with something very simple, which is kind of where are we going? Where do we have to deliver? Again, on benchmark instances, we already given like exact coordinates of everything that we have, and we know exactly how much it takes to drive from place to place. In practice, things are a little bit more complicated. So what we start with are addresses. So we can have an address that says, oh, it's on 123 Main Street, or in some geographies and in some markets, you may have something like you give a town and then you give a descriptor of the kind of, it's on the red house next to the school. And these are real things, and in some areas, that's how addresses are described, and everybody kind of knows what it does. Like if the post office goes there, they know where to deliver. So we have to find a way of translating these things into actual geocodes, into latitudes and longitudes. And most importantly, we then need to map this onto the road network, because we have to ask someone to drive to a certain location on the road network. So we need good map data with not only good a good description of the geometry of the road network, but also the topology of the road network. So how things connect to one another. Once we have these locations, we don't really ask people to drive to each individual location independently. So if you have like two deliveries to the same building, you probably just want to merge these two deliveries into a single stop, because there's an overhead in looking for parking and kind of leaving the vehicle and so on and so forth. If you have two houses that are just next to one another, you probably want to consolidate them into a single stop. So there's this stop consolidation operation that needs to happen, so that we decide what are the right stops to move people to direct people to. Even when we have the stops, our problem is not solved. So if you look at the pictures on the right, so suppose we know that we have to serve this one particular house. If this house is on a two-way street, you actually have two options. So you can approach from the same side of the street, or you can approach from the opposite side of the street. Of course, all else being equal, you always want to approach from the same side of the street. But depending on what comes after, what comes before, it may make sense for you to approach from the opposite side of the street and make a U-turn, or approach from the opposite side of the street, or cross the street, assuming it's a very local and safe street to cross. So as part of your optimization, you need to decide among multiple options of where to park, which one is best for that particular stop that you have. In practice, that means that whenever you're solving your vehicle routing problem, when you're looking at an individual route, you're not really solving a TSP. You're now solving a group TSP, because for every stop that you have more than one option, and you have to decide which option to pick. At the very least, you can do things like whenever you're using your favorite TSP like heuristic to solve or method to solve a particular stop, and you have to solve a particular route, and you have a sequence in mind, you can use a little bit of dynamic programming to pick for each stop in the sequence which side of the street to pick, or which option to pick. So these are the kinds of things that we have to worry about in practice when solving the problem. Once we understand what are the locations that we have to go to, what are the stops that we have to go to, the next thing that we have to decide is, if we have a route that we're considering as to be part of our solution, how do we decide if the route, if the amount of work in the route actually fits in the route? So one of the most important factors that we consider is how much time is spent on the route. So that means we actually have to have an accurate estimate of what is the total transit that happens in the route, like how long does it take to drive between stops in the route, and also the total service at each stop. So every stop is different. There is no, depending on where you go, depending on the type of location, depending on your go to a residential address, to a commercial address, to a large building, to a small building, if you're doing attended deliveries, or if you're doing unattended deliveries in which you can just leave a package on the porch, all of these things have different service times, and we kind of have to have a good idea of what they are in order to estimate the amount of work that we can put in a route that is reasonable for our drivers to follow. The challenge, that this is already challenging by itself, but an additional challenge is that the context may actually change. So depending on how experienced the driver is, they may be faster or slower. So if you have a driver that just started, we don't expect them to be as fast as a driver that has been around for some time. The familiarity with the area and with individual buildings also matters. So if it's the first time that you go to a building, you may not know how to access and so on and so forth. So we have systems that help people out, but nothing beats the fact that you've been to this building a few times before, you know exactly where to go to deliver a particular package. You may have routes with helpers. So instead of having just a driver, you have some other person to help the driver deliver. That will actually make deliveries much faster for that particular address, so the service time will change. And same for transit time. So transit time may vary with time of day, with traffic, with weather. These are all things that we need to consider when planning our routes. And this is just for time. And of course, there are many other factors that limit what we can put in a route. For instance, the main one is volume, like what is the space that the packages occupy. So if you have a small vehicle, you may fill up the entire van, and that will be the limiting factor. Or we can have a limit on the total weight that you can put in the vehicle, or the number of shipments that you can put in a route, and the number of stops. Time windows may also limit how long you can make the route. The distance driven may also be something that we want to limit. And in case of electric vehicles, and there's a lot of investment now in electrifying our fleet, battery range becomes another thing that we have to worry about. And the binding constraints differ within the plan. So different routes will be bound by different aspects among those that I mentioned. And this brings us to a new factor, another factor, which is heterogeneity and variability. So each plan by itself is very heterogeneous in the sense that we may have like dozens of different types of vehicles on the same plan. So they may have different capacities. They have small vehicles, large vehicles, electric vehicles, non-electric vehicles, and so on. You may have different driver capabilities. So some drivers may be able to do some kinds of deliveries that other drivers cannot. So we have to account for that when creating the plan. We may have multiple route departure times. We may have hundreds of routes in the same plan, so they all can't dispatch at the same time. So we have to account for that. We may have different shift times. So some routes may last 8 hours, some routes may last 5 hours, some routes may last 4 hours as a maximum input, as a maximum allowed input. We may have different delivery service partners. So delivery service partners are these independent companies that Amazon works with within each station. So a station will have different companies, and each company has manages their own fleet and their own drivers. But we have to create a plan for all the companies at once. And they kind of expect to have a certain part of the jurisdiction that they're mostly responsible for. We can do some load balancing and kind of move them around a little bit, but we shouldn't send a driver from a delivery service partner from a DSP that is generally in this area. We cannot send them to a completely different area on any given day. So these are the kinds of things that we have to consider. And as I mentioned before, driver familiarity and tenure actually varies a lot. So some drivers are very familiar with certain areas, less familiar with other areas. Some drivers are new, some drivers are more experienced, and all this goes into play when creating a plan. And this is only within a plan. There's also the issue that no two plans are the same. So even within the same station, there's a lot of variation across the week. So the density of where your packages are will vary on weekdays and weekends. So you can expect more business deliveries, more commercial deliveries during weekdays, for instance. Even between Friday and Monday, there will be some variability, so density will change and so on. There's variability across seasons. So as you know, there are like one or more peak seasons towards the year. So in the US, like around Christmas, between Black Friday and Christmas, volume is a lot higher than during the rest of the year. So the number of packages is a lot bigger than the rest of the year. So there are differences in density, there are differences in number of packages, the size of problems that we have to solve, and so on. And there are differences across the year. So as I mentioned, AMZL has been growing, so we do see a steady increase in density across different geographies. There are differences between geographies as well. So I live in the San Francisco Bay Area, a route in downtown San Francisco is going to be very different than a route in more suburban Silicon Valley, which will be different from from a route in a more rural like Napa Valley. And all of this, even within the same station, you may see these differences, and across stations, you see this even more. And there are differences across countries. So we did the kinds of deliveries and the kinds of constraints that we have in the US are different from what we see in Italy, which is different from what we see in Japan, which is different from what we see in Brazil. So these will all be different kinds of issues that we have to deal with. Another interesting thing that I learned as soon as I joined Amazon that I didn't expect coming from a more kind of theoretical algorithmic background is that whatever we do has to fit well with processes, and processes are like physical processes are much more complicated than I expected. In particular, as I mentioned, you can have very large plans with tens of thousands of shipments, and we can run the route planner and create beautiful routes on paper, but then someone has to go and physically sort packages. So you have a pile of like 50,000 shipments that you receive. You have to physically sort them into hundreds of individual routes, and that takes time. So a very large station, it may take many, many hours to do, let's say like 10 hours to sort all the packages into routes. So that means you have to decide what to do like the night before. But by then, not every package will have arrived at the station. So one thing you can do is you plan your routes for the packages that you expect to arrive at the station. So you know those packages are incoming. You have your systems that keep track of those things. So you know what packages are incoming. You run your route plan before these packages arrive. As the packages arrive at the station, you start sorting them to route. So that would work, except that the packages that arrive at the station may be different from the packages that you planned for. As I mentioned, you have these big trucks coming in. Each truck will have like 5,000 packages. If one of those trucks is late or it doesn't arrive, you will have planned for routes that assume the packages in those trucks will end up in your van. But if the truck doesn't arrive, your route was going to be short. But you're already like committed to those drivers, etc. So this is actually going to be very inefficient. So an alternative to that, and that's something that we often use for very large stations, is instead of sorting to the routes directly, we kind of delay route planning as much as we can. And we do so by essentially running an intermediate stage the night before, which is what we call container planning. What we do is we take the jurisdiction, we split the jurisdiction into very small zones. So these are small areas that may have an expected, the small areas in the geography that will have something like 20 packages expected for that particular day. We're going to have thousands of those across the station, across the jurisdiction. Each one of them will be mapped to a bag at the station. So think of a container as you see in this picture here. So there are there's a wall of containers there. As packages arrive at the station, you kind of know which container it has to go to. So when that happens through the night, so you start putting those bags in those containers. Early in the morning, you start putting the packages in the containers. Early in the morning, once you've received all packages at the station, you stop inducting new packages, you stop receiving new packages, and then you run route planning. And now route planning will run on bags. So basically each route will be a collection of bags rather than being a collection of individual packages. The advantage of this is that you have perfect information because you know exactly which packages are at the station, and you have faster picking. So instead of having to move 200 individual shipments to a route, you now have to move 10 bags to a route, which is a much faster thing to do. So that's nice, but it does impose extra constraints on routing. Now you are not free to assign any shipment to any route. Now you have to assign entire bags to a route. You still have freedom to sequence those bags however you want, although with certain constraints on you don't want to kind of switch between bags too often, but you don't have as much freedom as you have with a full sort to route world. And this is just one example of how routing is related to other processes in fulfillment. So in this example, I mentioned sortation planning or container planning. But after routing, which happens before routing, but after routing, you have things like dispatch planning. You have to decide in which order the routes will actually be dispatched from the station. There is before routing or before container planning, you have to do labor planning. You have to decide how many people will show up to sort and how many people will show up to drive for that particular day. There's network planning, deciding where the stations are and what the jurisdictions of the stations are. And all these decisions are interdependent, and they are something that we have to worry about. Now going back to more of the algorithmic part of things, one problem that we have, or one challenge that we have, is scaling. So we have to solve extremely large VRP problems. As I mentioned, they can have tens of thousands of shipments, sometimes over 100,000 shipments that we have to plan. And as I explained before, route planning is on the critical path of what we do. So basically, after every packet is at the station, we run route planning, and then we start picking the bags to the route. So route planning has only a few minutes to run. And that's very challenging. So even computing, for instances of that side, even computing the input. So suppose you need a transit time matrix as input to your VRP computation. Computing that matrix and starting that matrix in a naive way would be too expensive. Of course, luckily we have Dimax challenges, so we can look at whatever kind of work happened in the 9th Dimax challenge on shortest paths. It can actually be used to make this computation more effective. Also, the 10th Dimax challenge, which was on partitioning, actually helps the techniques that were presented on the 9th Dimax challenges. So my recommendation is always attend Dimax challenges. They will solve all your problems in due time. After we have these inputs, after we computed all these things, then we use some combination of mathematical programming and combinatorial heuristics to find a reasonable solution to the problem. Of course, for a problem of this side, we won't even pretend that we can reach a globally optimal solution to this, but we do need to find a clean, good-looking solution to the problem. And the reason for that is people, which I think is one of the most important part and one of my most important learnings since joining Amazon. One interesting thing about vehicle routing is that it's an optimization problem that doesn't happen in a vacuum. Every route that we generate, there will be someone that will go and try to execute those steps that we ask them to do. So there's a lot of visibility, and there's a lot of auditing happening for the results that we generate. So of course, the drivers themselves are the first ones that will look at it, but operators at the station, the delivery service providers, even leadership, like the managers and VPs and CEOs that own the system, can look at each individual route, and if something is wrong, they will notice and they will complain. So in practice, what we notice is that plans should not only be efficient, but they should feel efficient. So if someone looks at a plan, they will have very strong opinions on whether the plan makes sense or not. And they have strong, although somewhat fuzzy requirements that they have. For example, they want routes to be compact. They don't want a route to be kind of all spread out all over the place. They want routes to be well separated. They don't want like multiple people to go to the same area. They want like the one driver to go to the same area. They want routes to be clustered by provider, as I mentioned before. So you have one DSP that is responsible for a certain area. You don't want to have like multiple DSPs in the same area, or the same DSP kind of spread out over the entire network. And they want routes to have no backtracking. So the route should feel like you have a flow to it, and you're not going back to the same location multiple times. You want routes to be consistent across days, and so on and so forth. The problem is, like, if you look at the optimal solution to the standard definitions of CVRP and other VRP-related problems, like the one you see on the right, they don't actually obey this thing. Like, so the area that I circled on the right, they're actually like a bunch of routes that are clustered in the same area, and people look at this and say, this isn't efficient, this can't be right. And we can show that this is the optimal thing to do, but you're never going to convince people of that. It's because they actually, and that actually makes sense, because what they're thinking about is our proxies, not only for efficiency, but for robustness. So if something goes wrong, they want it to be very easy to recover from it. So if the routes are all spread out and you cannot deliver it to a particular address because the customer is not home and you want to come back later, if the route is spread out, that's harder to do. If the route is compact, that's easier to do. If they need to change something, having a compact route is a good thing to have. So drivers will always fix our mistakes. So if we don't have a right model, the drivers will deviate and will do their own thing, and they will often be right when doing that. So it's very hard to get everything right. So the biggest challenge we have is perhaps finding the right balance between all those goals that we have. There's one hard constraint, which is like we only create routes that are safe. So, but once we take care of safety, meaning like we don't ask people to cross the street in areas that are unsafe, we don't ask people to turn against traffic or make a U-turn in areas in which that's not safe to do. But among all the safe routes, there are lots of different options that we can have, and like how do we prioritize among them? So this is my last slide. What are the lessons that I learned in my last 7 years at Amazon? I think the biggest one is we can't presume to know everything. I think we're planning routes in the real world, and the real world is very hard to model. So we have to be prepared for what happens. In particular, we need our systems to be agile, flexible, and extensible, our algorithms. So we can't ever over-design for the current state, for the current objective, because like a week from now, the objective will be different, or there'll be a different request for a different feature that we hadn't anticipated. So we have to keep our systems and algorithms pretty open-ended and pretty amenable to extension so that we can support that. Another lesson is that we have to be robust. Like, as I said, if we fail to generate a route plan, this will be very, very disruptive. So the station will not be able to deliver. They'll be stuck with like 50,000 or 100,000 shipments, and we're trying to deliver Christmas. So that's a bad thing to do. So if the input is imperfect or something else happens, we can't simply blow up. We have to produce some decent result and then go and try to fix this for the next day. Local optimality is crucial for trust. So if people look at your routes and say, I could do better by moving this here and moving this there, they would completely lose trust in your system. So even though we're not globally optimal, we should at least try to be locally optimal. And finally, and most importantly, listen to your customer, your users, which in our case is mostly drivers. They will deviate from our plans. They will think they know better. Usually they do know better. So basically what we can't be is prescriptive. We can't tell people do whatever we say because we know best, because we don't really know best. But our definition of success is when they don't want to deviate. So if we produce a plan and they obey the plan and they don't have to obey the plan, it means that we're doing a good job. That's all I have. Thank you very much.